Hi guys, welcome to the ANOVA chapter. So, you're an American merchant captain in 1784. The Revolutionary War just ended. You've been trading under the protection of the British flag your whole career, but now you fly the American flag, the new red, white, and blue. You set sail into the Mediterranean Sea, heading for a trade route your family has run for decades, and 3 days out, a ship appears on the horizon, flying a crescent banner, moving fast. They're not there to trade. Within an hour, your cargo is gone, your crew is in chains, and you're being marched into a North African port as a slave. The Barbary pirates have been running this operation for over 300 years. Spanish ships pay them off, French ships pay them off, British ships pay them off, everyone pays them off. And now you're not British anymore, you're American, which means no one is paying for you. This is where our story begins, and it's also, believe it or not, where a fundamental statistical problem begins. Because here's the actual problem hiding inside this historical disaster. When you have more than two groups and you want to know which approach actually works, how do you compare them fairly? John Adams said, let's deal with these pirates by paying tribute. Thomas Jefferson said, we do not negotiate with pirates, let's go to war. And then a man named Stephen Decatur eventually said something even bolder, park your cannons in their harbor and collect what they owe you. So 3 different strategies, 3 different possible outcomes, 3 groups. That's the problem we're solving today. So what is an ANOVA and when do you use it? You just watched 3 groups form in history. Morocco negotiates and signs. The Ottoman states refuse and demand money. Adams eventually pays. Jefferson refuses. 3 different responses to the same pressure. 3 different outcomes. Before we can test which strategy actually worked, we need to understand the tool and why it's the right tool for a situation with more than 2 groups. So ANOVA stands for Analysis of Variance. We're focusing on variance across groups, calling back to everything you learned about variance earlier in this course. So variance relies on the sum of squares, the sum of square deviations scores for a data set. So just a quick reminder, you've seen this before. That number tells us the total spread in the data, right? So hold on to that concept because it's fundamental to ANOVA. So here's when you use an ANOVA. Okay, why wouldn't you use other tests? So you need 3 things. 3 or more groups. Okay, ANOVA is designed for comparing more than 2 groups simultaneously. If you have 2 groups, you use a t-test. If you have 3 or more groups, you use an ANOVA. The second reason we use an ANOVA is you have a continuous dependent variable. So the outcome you're measuring, mood improvement, annual cost, career satisfaction, driving ability, those variables have to be measured on a continuous scale. Numbers that can take many values, not just categories. And then the third reason is a categorical independent variable. So we have a continuous dependent variable and then a categorical independent variable. So the groups themselves, unemployed, part-time, full-time, pay tribute, go to war, or deploy force. These are categories people belong to, okay? So in the Barbary case, our independent variable is going to be diplomatic strategy. 3 categories, okay? They're not continuous variable, they're categories. And then our dependent variable is going to be the annual cost imposed on American commerce. How well did those strategies work based on the cost to our economy? Okay, so a continuous outcome. The money is a number on a continuous scale. Okay, but then the independent variable are categorical groupings. 3 groups, ANOVA. Okay, continuous outcome, categorical grouping, 3 groups equals ANOVA. Okay, so before we go further, let's orient you. Okay, every inferential test you've learned in this course belongs to one of 3 branches, and knowing which branch you are on tells you what kind of data you're working with. Okay, so you have the means branch, the relationship branch, the frequency branch, okay? So the means, you're comparing averages. T-tests, ANOVA, okay? The outcome is continuous, and you're asking whether groups differ on that continuous measure. So this is where we are today, okay? We're in the means branch. And then just a reminder, we've got the relationship branch, whether 2 continuous variables are moving together or not, correlation, regression. Frequencies, you're counting how often things fall into categories. Chi-squared, we're going to be covering that soon. So ANOVA is the means branch extended, okay? So the t-test compares 2 group of means. ANOVA compares 3 or more. Same logic, same branch, just more numbers of groups. Everything you learned about the t-test, the null hypothesis, the sampling distributions, type 1 error applies here. ANOVA is not a new way of thinking. It's more of the same, but just scaled up to multiple groups. And then remember that every test shares the same skeleton, okay? So every inferential test you've ever run, the z-test, the t-test, ANOVA, chi-square when we get to it, follows the exact same 4-step skeleton. If you can see this skeleton, the formulas stop being a list of things to memorize and start being one idea just expressed different ways. So 1 is observation. You measure something. You collect data that produces a value, a sample mean, a set of group means, a frequency count when we get into the frequency branch. In ANOVA, 3 group means and the grand mean, which we'll talk about. So observation, then expectation. So based on the null hypothesis, you predict what value your observation should take if nothing interesting is happening, okay, if the null hypothesis was true. In ANOVA, if all groups are equal, the group means should all be close to the grand mean. The between group variance should be small. Don't worry if you don't understand those yet, we'll get to it. Then third bone on the skeleton is the distance. You compute the gap between what you observed and what was expected, okay, expressed as a test statistic. In ANOVA, that's the F ratio. It measures how far the variance is between groups from what you would expect under the null, okay, relative to the within group noise. But again, we'll get to that. Okay, so what's the distance between what I observed and what I expected? And then you make a decision. You compare the test statistic to a reference distribution to decide whether the departure from expectation is significant. In ANOVA, you compare your obtained F to the F distribution, okay, at your degrees of freedom and alpha of whatever you choose, 0.05 usually. Okay, so observation, expectation, distance, decision, that's the skeleton. Every test, every time. The formula changes, the distributions change, the skeleton never changes. All right, so we have null hypothesis and alternative hypothesis. So the hypothesis structure for any ANOVA will look like this every time, no exceptions. Null hypothesis, alternative hypothesis. So null hypothesis, all group means are equal. There's no difference in the outcome across any group. So you have mean 1 equal to mean 2 equal to mean 3, or mean 4, mean 5, however many groups you have. They're all equal. That's the null hypothesis. And then the alternative hypothesis is that they're not equal. Okay. It doesn't tell you whether one's bigger or not, but it tells you whether they're equal or not. Okay. So in plain language, like for our example with the Barbary Coast pirates, the null hypothesis would be there's no meaningful difference in the annual cost to the American economy across the 3 different diplomatic strategies. Okay, and then the alternative hypothesis again is that there is a difference. At least one group they may not all be equal, but at least one group mean differs. So notice what the alternative hypothesis does not say. It does not specify which group is different or whether it's higher or lower. That specificity is not something we can state in the initial omnibus test. And an omnibus test in statistics is a test that checks whether there is any overall difference or effect. The word omnibus is Latin for all or for everything, for everyone. The ANOVA only tells us that a difference exists somewhere. We will need follow-up tests, what we call post hoc tests later on to find out exactly where. And we're going to cover that in a later lecture. So this matters. The ANOVA is a blanket question. Are all these groups the same? And the answer is either yes, which is, retaining the null hypothesis, or if it's no, then you reject the null hypothesis. It's not asking which strategy is the best. It's not asking by how much. It's just asking, is there any real difference at all? Okay. Now, here is a rule, the alpha level rule, okay? There's no exceptions to it. For all ANOVAs in this course, we're going to be testing at alpha 0.05. Only 0.05, not 0.01, not 0.001. Why? Because the F table that we use is built specifically for alpha 0.05. So using a different alpha level requires a different table, which you can do, but we're going to keep it simple at alpha 0.05 every time, no exceptions, okay? So here's a question. You have 3 groups, okay, and you want to compare them. Why not just run 3 t-tests? Compare group 1 to group 2, group 1 to group 3, group 2 to group 3, 3 tests, 3 answers, done. Okay? This instinct seems right, but it's completely wrong. And understanding why it's wrong is one of the most important things you'll learn in this course. So let's say you're Congress in 1800, evaluating which of these 3 diplomatic strategies should we use. You want to know which pairs actually differ. What you're tempted to do is run a t-test comparing Spain's tribute approach to England's tribute approach. And the result might be 0.03, which is significant. Yay, okay. Then you run another comparing England to Thomas Jefferson's war approach, and the result is P equals 0.05, which is significant. Yay. And then you run a third comparing Spain to Jefferson, and the result is a P of 0.06. Oh, it's not significant, okay? Not quite significant. You found 2 significant differences. Your colleagues are impressed. You report the findings as if you've discovered something great. But here's the problem. Every time you run a hypothesis test, if your alpha is 0.05, which is what we're doing in this class, you accept that there is a 5% chance of a false positive, a type 1 error, okay? You got lucky 95% of the time. But what happens when you run 3 separate tests? Each one has a 5% chance of being wrong. So 5% chance of being wrong with this one, and a 5% chance of being wrong with this one, and a 5% chance of being wrong with that one. So what's the probability that at least one of them is wrong across all 3 tests? It's not 5%. Okay, let me show you the math. The probability of being correct on test 1, okay, probability of being correct on test 1 is 95% because you have a 5% chance of being wrong. The probability of being correct on test 2 is also 95%. Probability of test 3 is also 95%, okay? Now to get your probabilities, if you remember from the probability chapter, you have to multiply those. So you multiply 95 times 0.95 times 0.95. That's how you get probabilities, okay? That equals to roughly 0.857 or 86% of the time you will be correct, which means the probability of getting at least one false positive, of being wrong, is 14%, okay? 100 minus 86 is 14. So run 10 comparisons, and that risk climbs up to 40% chance of being wrong. You're essentially running a rigged game. The more tests you run, the more false victories you claim, the more false positives. Not because you found something real, but because probability just caught up with you. So this is what statisticians call the multiple comparisons problem. Okay? It's not a technicality. It's not a minor issue you can ignore. It's a form of intellectual dishonesty, okay? Accidental, maybe, or deliberate. It happens constantly in published research. It helped cause the replication crisis in psychology. Many findings that seemed significant and real turned out to be false positives produced by researchers who ran multiple tests and reported the ones that looked good. So Jefferson just ran an entire presidential campaign on a hypothesis. His null hypothesis was atoms. Paying tribute is an acceptable equilibrium, okay? Paying tribute is good, okay? His alternative hypothesis was his own platform. Force will produce a different outcome. Okay? Force is good. Which means and he won the election, which means the voters preferred his alternative, okay? Now the data has to decide. Okay? This is the thing with politics. It's not your opinion. You have to actually look at the data, do the research, understand the statistics. To evaluate that hypothesis statistically, we need a test statistic. And to understand what that statistic means, you need a picture of the distribution, okay? So the F distribution is always positive. Okay, because it's either, well, maybe I should put 0 here. It's always either 0 or positive because the F is a ratio of 2 variances, and variances are always 0 or positive, right? Because you're squaring to get rid of the negative. So the distribution is skewed to the right. Most values cluster near 0 or 1, but there's a long, thin tail that extends out towards large positive values. So this is why ANOVA is always technically a one-tailed test, even though we never talk about that because it's just assumed for an ANOVA. You don't have 2 tails, so it's always a one-tailed test, okay? We never talk about tails when we're deciding on alpha. we're always looking out in that long right tail. If our F falls far enough into that tail, into what we call the rejection region, then we reject the null. If it doesn't, then it falls into what we call the retention region, and we retain the null hypothesis. To find your critical F value, okay, you need two things: your degrees of freedom between groups and your degrees of freedom within groups. So these are different from each other and both are required. Let me give you a quick reminder of what these mean. So you've hopefully watched my video on degrees of freedom, so I'll keep this brief, but it's important to refresh you because you'll use these formulas immediately in this course. So you have your degrees of freedom between groups, and the formula for that is G minus 1. Okay, G is the number of groups. So it's no different than the regular degrees of freedom formula where it's N minus 1. Okay, absolutely no different. But we use a different letter because we're not talking about just individual values. We're talking about numbers of groups. So it's, the formula is the same, but we're just using kind of different, not different vocabulary, but different, well, hopefully you understand what I'm trying to say. Okay, N and G, you're calculating things the same way, but instead of using individual values, you're using numbers of groups. So in the Barbary example, we have 3 strategies. Okay, so 3 groups, three groupings of strategies, right? So the degrees of freedom between groups would be 3 minus 1, which now equals 2. So that would be the degrees of freedom between groups. So the intuition with this is if you know the grand mean, which is the overall average from all groups. So you have the mean of group 1, you have the mean of group 2, you have the mean of group 3, and however many groups you have. And then the grand mean is all of these groups, added together and then divided by how many groups there are, which in this case is 3. So if you know the grand mean, and you know 2 of the 3 group means, the third group is determined, right? That's what the degrees of freedom means. If you know 2, so you have, let's say this is A plus B plus C. So A plus B plus C divided by 3 total equals the grand mean. Okay, I'm just going to write it like that for now, the grand mean. So if you know what A is, and you know what B is, then C is automatic. A and B could move around. They could be different numbers, but C is going to be locked in stone if you know what A and B are. Okay. If you don't understand that, go back and watch my degrees of freedom video. It's very easy. It just means that when you know when you know all the variables except for one, that last one doesn't have a choice of what the value is. Okay, mathematically speaking. Okay, so that's why it's G minus 1. Okay, so then we have the degrees of freedom within groups. Okay, and that is the value minus the total number of observations minus the number of groups. Okay, so if we have 18 total observations and we have 3 groups, then the degrees of freedom within equals 15. Okay, so the intuition with this represents the degrees of freedom left over after you've estimated a mean for each group. So within each group, once you know the group mean and all but one of the scores, the last score is determined. So you lose 1 degree of freedom per group, hence N minus G. And again, if that's confusing, just go back and watch my degrees of freedom video with Harry Houdini and all that. It's interesting anyway, so hopefully that will explain it to you. All right, so how do you read the F table? The F table has the degrees of freedom between across the top row. That's the numerator. It has the degrees of freedom within down the left column. That's the denominator. You find the cell where your row and your column intersect. That's your F critical. So we always write degrees of freedom like this. Our F is degrees of freedom between, comma, degrees of freedom within, just like correlation intervals sort of idea. So for our Barbary example, f of 2 and 15, that's what we just calculated, right? You remember all that? Okay. So this is our where's it here? Degrees of freedom between groups, degrees of freedom within groups. So this is how we would write it out. So in the F table, go to column 2 and go down to the row 15 and read the value in that cell. And then again, remember, in this course specifically, alpha is always going to be 0.05, no exceptions, okay? Alpha 0.05. So for F215 at alpha 0.05, the critical value, F critical, is 3.68, okay? Always write that down, make a note of it somewhere, highlight it, whatever you need to do to keep track of it. If our obtained F exceeds 3.68, that's in the rejection region, okay? So if you draw your distribution, 3.68 is the beginning of the rejection region. So if our F value is above that in the rejection region, then that means we're going to reject the null hypothesis. If it's not, if it's in the retention region, then we retain the null hypothesis, okay? It's very simple. So remember the picture of the F distribution. Your critical value of 3.68 is that vertical line you drew towards the right tail. Everything to the right of that line is the rejection region where we'd conclude that the groups are different. Everything to the left of that is the retention region where we'd conclude we don't have evidence of a difference. So your obtained F is going to land somewhere on that curve, and then you'll make your decision based on where it lands. Now let's talk about something, we've talked about this before. Signal and noise, okay? So everything in statistics, t-test, correlations, ANOVA, regression is ultimately about one question. Is what I'm seeing a real signal or is it just noise? So imagine, you know, you're listening to this tone, just do, but then you've got white noise, okay? It's very, very small white noise, but it's getting louder, louder, and louder, and louder, and eventually you can't hear that tone anymore. The noise is obscuring the signal, okay? So is what you're hearing, is it the actual tone, or is it just the noise that you're hearing, the variation? That's what statistics is all about. So ANOVA makes this question completely explicit. It doesn't hide the logic and formulas, it puts the logic right in the structure of the test, and we'll go through that. All right, so let's look at the setup for our test. You have 3 groups of American diplomatic strategies spanning different eras. So you measure the annual cost of Barbary piracy to American commerce under each strategy. Okay, so the 3 groups, you've got group 1, I'll put like G1 like that, is pay tribute forever. Okay, that's the Adams approach. And the annual cost of that is $83,000 a year. Group 2 is declare war and use the Navy. War and Navy. And that's the Jeffersonian approach. And the annual cost of that was $40,000 a year. Now remember, this is 1803-ish. So that was a lot of money back then. Okay. And then group 3, deploy overwhelming force on the land with the troops, collect reparations, make them pay us back. That was the Decatur approach, Stephen Decatur. So, and then what's the annual cost of that? It doesn't cost us anything. It's $0. So the means are different. The averages are different. The Adams years, okay, are expensive. The Decatur year is 0. But here is what ANOVA asks before we get excited. How much of the variation in those costs is explained by the strategy itself? And how much is just random year-to-year noise? Okay, that's what we need to do. No, because this was over time, the economy changed, inflation changed, and so on. Is this random noise or is there something significant to this? Okay. So There's two sources of variability. So imagine spreading out all your data points across all three strategy areas. They vary. Some years are worse than others. Some negotiations fail unexpectedly. Some pirates get more aggressive or sail less aggressively. There's noise in the system. ANOVA splits that total variability into two buckets. Okay, you've got two buckets here. Those are buckets, believe it or not. Okay, so bucket one is between group variability. Okay, how different are the three group means from each other and from the grand mean of all three of them? If strategy matters, this should be large. The Adams mean, the Jefferson mean, and the Decatur mean should be far apart. Okay? In our case, it's pretty clear, right? You've got 83,000 versus 40,000 versus 0. Okay, these are very far apart. So this is an obvious example. I'm trying to make it obvious so that it's clear to you how this works. Bucket 2 is within group variability. How much do the scores vary within each group? Year-to-year noise, things outside anyone's control. This is the baseline noise level. This is the white noise that might obscure your signal that you're listening to. Even if the strategy is constant, annual costs fluctuate. Some years the weather's good and the pirates are more successful. Some years the weather's bad and the pirates are less successful. There's less merchants going out in their ships. There's more shipwrecks and the pirates don't even have ships to get. How much variance is there? How much variability within each year? Some years diplomatic negotiations go better than expected. Okay, so in our case, within the Adams years, costs don't vary widely year to year. Within the Decatur years, they're all 0. There's no variation. So this is relatively small noise. So this is a very clear-cut, easy example for you guys. All right, so here's the conceptual core of ANOVA. Okay, make sure you take notes of this. So the variance total, or the sum of squares total, remember that means the same thing, SS equals variability, okay? Sum of squares total, you're not going to be surprised to know that it's the variance between groups plus the variance within groups, okay? So this bucket between groups plus this bucket within groups. That equals the total. Okay, so the total variability equals between group variability plus within group variability. Okay, so you think about like how different are my friends and I. So the total variability between you and your friends would be how different is each person from each other, as well as how different is your group from other groups. Okay, so the whole equals the sum of its parts. This is called partitioning the variance. Okay, those are R's. Partitioning the variance. So partitioning means dividing up. So the variance is divided or partitioned into bucket 1 and bucket 2, partitioning the variance. Now ask yourself, if our strategies with these pirates has no effect, if the null hypothesis is true, if all three approaches produce identical results, what would we expect with variability? Okay, think about it. Pause it and think about it, because if you can come up with this answer yourself, then it'll stick with you more. If strategy has no effect, if all three approaches produce identical results, what would we expect with the variation? What would we expect with the group means? Pause. We would expect, pause if you haven't done this, the group means to be similar to each other, okay? For there to be no real difference. Any difference between them would just be sampling noise. SS between, okay, the SS between should be small relative to SS within, okay? There shouldn't be a big difference between them. The signal of the strategy differences are buried in the noise, okay? If we go back to our little, noise thing, then there's really no difference between the signal and the noise. You're not seeing any difference. You can't hear the signal because there's so much noise. That would be the variability if there's no difference between the two, okay? But if the strategy does matter, if Decatur's approach genuinely did produce different outcomes than Adams, the group means should be far apart. The variance between should be large. The signal should be bigger than the noise, okay? Even though the noise is loud, the signal is really loud, or maybe, you know, the signal is loud, and then the noise is pretty small. So you can tell the difference between the signal and the noise, okay? If there's genuinely a difference, you can tell the difference between the signal and the noise. Okay, so that ratio, signal to noise, is the F statistic, okay? So the F statistic is the ratio of how much signal is there to how much noise, okay? So F is the between group variance, okay, divided by, just put that in parentheses, between group variance divided by the within group variance. Okay. That equals signal divided by noise. Okay, so the signal is between group variance and the noise is within the group variance. Okay, if you're wanting to know how different is my group of friends from other groups of friends, you would want to know what's the signal is the difference between the groups of friends. But there's a lot of variation between people in the group. And that makes it hard to say, is my group really different than other groups? And that's the within group variance. Between groups is the signal, within groups is the noise. Okay? If the signal is much bigger than the noise, F is going to be large. Okay? If and we can conclude that the groups differ. If the signal is similar to the noise, if F is near 1, we conclude that we don't have evidence for the groups to differ. So the bigger this fraction is, okay, if we look at this fraction, signal over noise, the bigger that fraction is, the bigger the F value, because this is an F value, then the more we can conclude that there is truly a difference, because there's a lot of between group difference, between group variability, and little within group variability. Okay, hopefully that's making sense to you. If not, comment on the video and I can go into it in more detail. Okay, so let me show you the logical sequence from partition variance, the buckets, to getting to that F ratio, getting to your F score. And this is the thinking behind all the formulas that you're going to see in the next lecture. We're not doing the calculations yet. We're going to be doing the calculations in the next lecture. So we're just going to go through the steps without doing any of the math, okay? So step 1, oops, I'm doing it in red this time, I guess. You're going to partition the variance. I don't know, what am I doing here? Partition. I can't write on this thing sometimes. Partition the total variance, I should say. Partition the total variance. So you have all your data points, right? Some are expensive, the Adam years. Some are cheap, the Jefferson years. Some are free, the Decatur years. The total spread of all these numbers, that's the SS total. Okay, you're putting them into the two buckets. You're partitioning the variance. So now you ask how much of this spread is because different groups have different means versus how much noise is just within each group. How much variation is there within the Adams years versus the Jefferson years versus the Decatur years. Okay, so you have to split the SS total into the two buckets. You have to partition the variance. And the two buckets are the variance between groups and the variance, that's an S, within groups. Those are your two buckets. You remember my beautiful buckets here? Okay, you have to partition into your two buckets. The spread explained by group membership, and the spread within the group, the noise, okay? The signal and the noise. You have to partition those two, okay? And we're going to go through how to do that in the next video, in part 2, okay? Part B. But step 1 is you're putting everything within the buckets. How much noise is there? How much variance is there between groups? How much variance is there within groups? Put it into the bucket so that you can know. Step 2 is, I wrote 2 step. Step 2 is you're going to account for the degrees of freedom. Okay, so here's the problem. If you have 100 data points, your sum of squares, your variance, will naturally be bigger than if you have 10 data points. Okay, the more things you look at, the more people in your group, the more whatever, the more variation you're going to have. The sum of squares is going to be bigger. Even if the data is equally spread out, it will naturally be bigger the bigger your group is. So you can't compare SS between directly to SS within. They have different amounts of data behind them. Okay, so the solution is to divide by the degrees of freedom. So we're going to be calculating the mean squares. Okay, now what is the mean squares? Simply, it is the sum of squares divided by the degrees of freedom. Okay, so you can think of a mean square as a kind of variance estimate. Okay. So why are we doing this? A sum of squares gets bigger as variability increases or you have more data points, right? And more data points causes more variability to happen. Dividing by degrees of freedom normalizes it. So we get an average amount of variation. We're trying to figure out what is the average variation. We don't want to just look at variation. We need average variation so that we can compare these two different buckets. That's why it's called a mean square. It's the average square. It's the average of the square deviations. Let me write that down. It's the average of the squared deviations. Again, if this isn't making sense, leave comments so that I know what to explain more to you guys. Okay, so in ANOVA, there's two main squares that we look at, which won't surprise you, the mean squares between and the mean squares within. We want to find out what's the average variation of each bucket. We're just figuring out what's the average in the buckets. Okay, we've got our two buckets. How much is within them on average? How much variability, how much sloshing around of water is there between each bucket? So we have the mean squares of the between bucket, and we have the mean squares of the within bucket. Okay, it's very simple. And again, it's just SS over degrees of freedom. Okay, the variance or the sum of squares over the degrees of freedom. So the formula for getting the mean squares between is you just get the SS for the between bucket and divide it by the degrees of freedom, and you get the SS of the within bucket and divide it by the degrees of freedom. Okay, it's not really two separate formulas, okay? It's really the same thing. Oops, that's way too big. It's really the same thing. It's just SS above degrees of freedom, okay? But you're making sure that you're doing the between and you're doing the within, okay? It's very simple. It's not two separate formulas that you're looking at. And you're really just doing an average. You know, the values divided by the total number of values. The total of the values, the sum of the values divided by the total values. That's basically what this is. It's the average of the variance, okay? And what this does when we take the average is we put the buckets on equal footing. So the mean squares between tells you how much groups vary in a standardized way. So the mean squares between tells you how much groups vary, how loud the noise is in a standardized way. The mean squares within tells you how much noise exists in a standardized way. So the whole point of step 2 is I'll put it here, you are standardizing so that the two buckets can be compared. Okay? And they're not apples and oranges anymore. They're now just buckets. Okay, now step 3, you're going to do the ratio. You're going to find your F score or your F ratio, okay? So, remember what we said before, the F score is the signal divided by the noise, okay? And what was the signal and the noise in this last step, okay? The signal is the ms between, okay? That's the signal. And the ms within is the noise, okay? So if the formula for F is signal over noise, then we know that this formula for F is the mean squares between, I'm just going to write that because I'm running out of room, divided by the mean squares within. That's not official formulaic vocabulary, okay? It's just because I'm running out of room. All right, so the formula for F is signal over noise. Signal divided by noise. The signal-noise ratio. That's why you call it the F ratio, or the F score is the F ratio. And signal is between groups, because we want to see if there's differences between groups. Noise is all the stuff going on within groups. So ms between versus divided by ms within. Signal to noise ratio in its cleanest form, okay? So step 3 is to find the ratio. So when the null hypothesis is true, if the null is true and all groups are equal, there's no differences between groups. Remember, mean 1 equals mean 2 equals mean 3 equals mean 500. They're all equal. Then both ms between and ms within have basically the same variance, okay? There's not going to be much of a difference between those two. And if you look at the ratio, which is the same thing as fraction, then it's going to equal roughly 1, okay? There's no difference between them. If this is 100, this will be 100, okay? Which equals 1. 100 divided by 100. If it's, I don't know, 49 between, it's roughly 49 within. 49 divided by 49 is 1. Okay, so the ratio that says there's no difference is roughly 1. Now, when we do roughly, just a quick little note here because you'll see this and be confused, we do it like this. Okay, so it's not going to be exactly 1. There's always a little bit of noise, but it's close enough. Okay, so, and then of course in the distribution, your F lands in the retention region. Okay, of the F distribution. And so we are retaining the null. We're saying the null is true. If we don't retain the null, if the null hypothesis is false and the groups really are different, so you're going to see that at least one of these does not equal. Maybe 2 don't equal. Okay, maybe they're all not equal. So then the ms between is going to be larger. It's going to be inflated by real differences. There's going to be serious, actual differences between the groups. And then the ms within, the noise, it's still just estimating the baseline noise. And if there is truly a difference, there's going to be a big difference in that ratio. The ms between is going to be much larger than the ms within. And so that ratio is going to, it's going to become much bigger than 1. Okay? This is going to be much bigger than 1. Now, what that is, I don't know. That's what we're going to calculate. But it's going to start moving your F score into that right tail that says that into the rejection region where we say we reject the null hypothesis. There is truly a difference, okay? And we'll find out what that rejection region is with our critical F value. Remember, we'll look that up in our F table. So if this is, you know, I don't know, 5, just pick a random score, and this ends up being, I don't know, 5 over 1, which equals F score, an F ratio of 5, then now your F is, it's significant. It's gone into that rejection region. We say the null hypothesis is dumb, it's not true. We're going with our alternative hypothesis. Okay, and that's it. It's very easy, okay? And is very similar to all the other tests that you've done so far. It's similar to the Z-score test. It's very similar to the T-test. We're just going into a new version with the ANOVA, which is basically an F test, but we call it an ANOVA because we have to be fancy. And so that's it. Okay, conceptually, it's very easy, and the mathematics aren't that much more difficult either. The formula are very similar to each other. If you understand why the formulas are how they are, there's a lot of similarities between them, and you can, if you take some time to think through the concepts, you can, instead of just rote memorization, you can actually understand them, and it's going to be much easier to remember what those formula are. Okay, so let's step back and see the whole picture we've built today. Okay, so the questions we're asking, we have 3 groups. We want to know if they differ. And the challenge is we can't just run 3 t-tests because that inflates our type 1 error, our false positives. So we need a single test that compares all 3 groups fairly. And the solution to that is the ANOVA. ANOVA answers the question, is the between group variance, the signal, large enough to exceed the within group variance, the noise? Does the signal exceed the noise? Can you hear the signal over the noise? Is the signal big enough, volume high enough that it outperforms the noise? Okay, and this is captured in the F ratio. F equals the signal over the noise, the signal divided by noise. Okay, how do we know if the F is large enough? We have to compare our F ratio to an F distribution. So that F distribution, just like the z-score and t-score and everything, it will show us what F value we'd expect if the null hypothesis were true, if all groups were equal. And if the F score that we get falls into the tail, that right tail of the distribution beyond the F critical score, then it's unlikely that that score happened just by chance, right? Only 5% chance that it got into there, because remember, we're using an alpha of 0.05. If we use an alpha of 0.01, which you can do, but we're not doing in this class, then there's only a 1% chance that it got into that tail above our F critical score, right? So we have to reject the null hypothesis. It's too unusual to have happened just by chance, okay? So let me draw the distribution just one more time, okay? And then we'll go through the logical chain, okay? So you have your distribution, and then you have the small area. This is a 5% chance, with our alpha of 0.05, 5% chance of an F score landing in that tail, which means that it wasn't by chance, okay? That's too rare for it to have happened by chance. Okay, so let's go through the logical chain. Step 1, we have our hypotheses. Okay, our groups might be different, our alternative hypothesis, or they might not be different, our null hypothesis. And then we collect our data to see if our hypothesis is true. We collect measurements from at least 3 groups. Okay, 3, 4, 5, 1,000, whatever. That's the ANOVA. But it's more than 2. Otherwise, we just use a t-test. 3, we have to now partition them into buckets of the between groups and within group variance. Split the total variation, the total variance, into between group and within group. We bucketize them, okay, partition them. And then 4, we need to make sure that they're standardized, okay, that we're comparing apples and apples, not apples and oranges. So then we're going to convert to mean squares to control for degrees of freedom, okay, to make sure that we're comparing them in a similar fashion, okay. Standardize. 5th thing that we do is we figure out our ratio. We compute the F score, and remember, F is signal over noise, okay? And then we compare. We look at our F table and find our F critical score. Is our F ratio, is our F score larger than our F critical score? And then we make a decision. How have I forgotten how to spell decision? Decision on whether we reject the null or we retain the null. Okay, if there is a difference, if the F falls into that long tail, then we reject the null. If it doesn't, if it stays in the main area, we retain the null. Okay, so think about this in the Barbary case. Between group variance was huge. The Adams mean of 83,000, the Jefferson mean of 40,000, the Decatur mean of 0, very far apart. Okay, so this is a very obvious case for the ANOVA. When you calculate how far each group mean is from the grand mean, okay, squared and summed, you get a large number. The SS between is very large compared to the SS within. The within group variance is small, okay? Within the Adams era, costs don't fluctuate. Within Decatur, cost doesn't fluctuate at all because we're paying 0 to the pirates. The noise floor is very low, okay? So this has a huge F score, a huge F ratio, okay? So the F ratio is going to, signal over noise, is going to be large over very small, okay? Which is going to equal to a very large F ratio. It's going to be a great F ratio, okay? And we'll see that it's, I mean, you can guess just by looking at those numbers, right? It's going to be in the far right tail of the F distribution, and which makes it extremely unlikely to have happened if the null hypothesis were true. To be spending that much money when the null hypothesis is not true would be crazy, okay? So, or when the null hypothesis is true would be crazy. So we reject the null hypothesis. The signal is screaming in this matter. The strategy obviously matters. All right, so now let's look at what you understand. So what is the ANOVA? The ANOVA is the analysis of variance. It's a test for comparing 3 groups simultaneously. It follows the same logic as t-tests, but it extends to multiple groups, okay? And why we use it is because it controls for type 1 error, the false positives, okay? And it doesn't inflate the chances of getting an error like multiple t-tests would. You use it when you have 3 or more independent groups and a continuous dependent variable, which is the outcome variable, and then categorical independent variable, which is our group membership. Okay. The multiple comparisons problem, you should understand now, that's running multiple t-tests inflates the type 1 error. Okay. 5% becomes 14% error for 3 tests, okay, and even more error for 4 tests and 5 tests and 6 tests. So the ANOVA solves this by asking one unified question instead. Then you should understand the F distribution, which is, it's always positive, right skewed with a long tail to the right. With the null hypothesis, your F ratio should be basically 1, okay, inside the bulk of the distribution, and with an alternative hypothesis, the F is large and way out in the right tail. So we look at the right tail only. It's always a one-tail test. And in this class, we're always going to do 0.05. But that's just this class, just so that you understand that. Then we have to understand our degrees of freedom. If that is confusing to you, which I understand because as a student, it confused the heck out of me, go back and watch my degrees of freedom video. So the degrees of freedom between is G minus 1. So the grand mean minus, or I'm sorry, the number of groups minus 1. The degrees of freedom within is the N minus G. So the total observations minus the number of groups. Okay, and both are needed to find the F critical from the table. And then you should understand signal versus noise. So between group variance is how far apart group means are. That's the signal. Within group variance is how spread out scores are within the groups. That's the noise. And the F ratio is going to be signal over noise. A large F means the signal it way exceeds the noise and the groups are most likely different. An F near 1 means that the signal is roughly equal to the noise, so there's no evidence of group differences. Okay, so the logic is always the same. Observation, expectation, the distance between what we observed and what we expected. So how far apart are they actually? Is between group variance larger than within group variance? And then you make a decision based on the critical score, the threshold for statistical significance. Okay. All right, so here's just a few things to ask yourself to make sure that you understand these. Can you explain the multiple comparison problems? Why can't you run 3 separate t-tests when comparing 3 groups? Describe what the F distribution looks like and why. What does it mean that it's right skewed with a long tail? And so on, okay? So if you can do these 6 things clearly, then you're ready to go on to part B. Okay, so now you understand why ANOVA works and what it's testing. You understand the logic deeply enough that you hopefully can explain it to someone else. If you can't, then learn to do that. But you don't know how to calculate it yet. So next part of the lecture, we're going to walk through every step of the calculation, which of course always looks intimidating at first, 7 steps with lots of formulas, but each one builds on the one before and on the t-test and even z-scores that we did before. So by the end of that lecture, you'll be able to calculate an F statistic from raw data, make a decision about whether your groups differ or not. And then in the lecture after that, we're going to talk about what the results mean, because getting a significant F is not the end of the story. It's kind of the beginning of the story. So for now, just sit with this conceptual understanding, this conceptual foundation. Make sure that you understand why we use ANOVA instead of multiple t-tests, what the F ratio represents, why the F distribution looks the way it does, what it means if F is large versus small. Okay? And then next time we'll calculate.